Thanks. So that's the talk. That's the title of the talk. I'm a mathematical statistician at NIAD, and let me get back into my. There we go. And before I start, I think it's important to acknowledge my co-authors here. So we have a bunch of co-authors here at NIH. Keith Lombard and Emily Ricotta worked really hard on this, and then at the University of California in Irvine, Damon, Isaac, and Vladimir all contributed immensely to this project and are also largely responsible or deserve credit for a lot of what's in this talk, but I'll take the blame. And so without further ado, what was our motivation here? So there are many SARS-CoV-2 transmission models that have come out in the last few months, and here there's a huge variety of methods and data sources. And so we kind of were wondering, well, what could we contribute? After all, we're not the biggest group. We're certainly not the best resource to do these sorts of massive models that we're seeing come out. But we were really interested in trying to understand how we could incorporate reported cases and tests into a model. And one of the things that we really wanted to do was account for changes in testing over time, at least try to figure out some crude way to do so. And the reason that this seemed to us to be an important thing that we could contribute is that in many cases, case data is the tip of the spear. It's, in other words, the earliest sign of an increase in transmission. So if you're hoping to kind of give people a heads up that SARS-CoV-2 transmission is going to explode in some area, then this might be your best chance to do it if you can kind of do it properly. But this data is also somewhat problematic in many ways. And so we had kind of felt that if we could also incorporate other data sources, we might be able to achieve more robust inferences. And so as a confession, we're going to really focus on these two issues of data assimilation and accounting for testing in a more principled way in this talk. Obviously, not every problem is going to be solved, and some things will have obvious ways in which they could be improved. And so here's how we kind of started on day one of quarantine, when we realized we didn't have offices to go into. And then when we started working on the project, there were some key decisions that we needed to make. First of all, what type of surveillance data were we going to try to analyze here? So cases, but then in addition to that, were we interested in hospital or ICU admissions or deaths? And then where were we going to get this data from? So public case counts, Lyme lists, outbreak investigations, and there are also different levels of granularity at which the data can be specified. So at the state level, county level, zip code, or for Lyme lists and hospital investigations, often that's available at, say, the household or hospital level. And so we had kind of started thinking about, well, maybe we were going to do some modeling sort of at the state level, and it turned out that we weren't really able to trust a lot of the data that we were seeing at the state level. There was just a lot that was kind of going into it that kind of felt a little suspicious to us, in the sense that we didn't understand what the protocols were for collecting data, and we certainly weren't going to be able to handle that kind of data at scale. So, for instance, modeling transmission in many different states. And then finally, we had to think about how were we going to model this? So what kind of tools were we going to use? And that's sort of downstream of all the other questions. But where we kind of settled was on an analysis of data from Orange County, California, where Vladimir and Damon and Isaac are, and many of their colleagues there were able to get line lists of anonymized data from the Orange County Department of Public Health. And this was actually really important because that line list data we were able to subsequently compare to some of the aggregate count data that was reported, say, on their public health dashboard. And we realized pretty quickly that there were big differences between these two data sources. And in fact, one of the things that we want to know when we're modeling transmission is how many new cases there are at any point in any given time interval. There were actually 10% more cases reported if you just look at the counts than if you got the data from the line list. So there's a big difference in data quality. And so we're going to focus our modeling efforts on transmission here. And then for various reasons, we're going to aggregate the data into 3-day time periods. This was kind of a good balance between temporal granularity and kind of smoothing out some of like the day-to-day noise. And so we're going to consider data from March 31st, 2020 until July 16th, 2020. So this is what the data look like. So we have this time series of test counts, a time series of case counts, and a time series of deaths. And one thing that's always important to keep in mind here is that actually we don't know the actual number of cases and deaths. We observe some fraction of incident cases and some fraction of deaths, but both of those are susceptible to underreporting. Furthermore, cases are preferentially sampled relative to incidence at the population level. So what this means is that the percentage of tests that are positive is greater than the percentage of the population that has been infected in some time interval. And these are both important dynamics that we need to keep in mind as we model this data. So a generative model for how did this data come to be, in our framework, we're going to do this in a Bayesian framework. So our data generating model consists of a transmission model, then a surveillance model, which basically describes the sampling distribution of the data given some latent epidemic process that's unobserved to us, but is estimated by the transmission model, and then a set of priors. And there's nothing particularly novel here about sort of the mechanistic transmission model that we used. This is, to our minds, simple enough to be more or less a realistic representation of the transmission dynamics. There are ways it could be made more realistic, sort of arbitrarily many ways it could be made more realistic, but we felt that it was sort of good enough here. So here, individuals in the population of Orange County initially start susceptible. Then due to contact that arises between susceptible and infectious individuals, they become exposed but have some sort of latent stage during which they're infected but not yet infectious to others. They then progress to an early stage of infectiousness that we denote here IE. IP is a progressed stage of infectiousness where people are possibly less infectious than in the early stage, either because they've become symptomatic or they're shedding less. And then from progressed infection, people either recover or remove, they isolate themselves or they die. And to represent the transmission dynamics, we use a system of ordinary differential equations. This is the infinite population limit of an underlying Markov jump process that is sort of a starting place for how these models often get constructed. And the key parameters in this model are, well, first of all, the now famous or infamous, depending on your perspective, basic reproduction number of the disease, of the outbreak, not the disease. I'm sorry, of the outbreak. The mean latent period, mean early infectious period, mean progressed infectious period, and the infection fatality rate. So really, we're most interested in the basic reproduction number and the infection fatality rate here. And in this model, R0 has this form that I've indicated here on the bottom, where beta is a per contact infection rate. And one thing that we have to know here is that both case data and death counts are incidence counts. And for that reason, it's really important to track changes in cumulative incidence of cases, that is IE to IP transitions, and cumulative changes in cumulative deaths. And so we use this redundant representation of the deterministic OD. So here on the left, we have sort of the canonical SEIR prevalence ODs, and on the right, we will have incident ODs that describe cumulative numbers of transitions throughout the process. And so solving these ODs, this gives us a really useful representation for incidence data, because we can solve only the incidence ODs that are relevant to, that we need to connect the data to the latent epidemic process, and then we can just difference those cumulative incidence paths. And then we have well-formed emission densities for the counts of interest. And so here we start getting into how do we connect different sources of data to a single latent epidemic model? And for mortality, this is sort of a standard surveillance model. So here we observe some count of the new deaths in a time interval, say T1, L-1 to TL. Rho here will be a mean death reporting rate. And we observe some fraction of the total number of deaths between times accumulated between times TL-1 and TL. And then in this negative binomial representation, we have this over dispersion. For instance, here's actually where we're going to, this is where we're going to start to contribute a little bit, because what we wanted to do, remember, is we wanted to account for tests, as we don't want our model to get confused between increases in testing and increases in cases. We want to always remember that we have some number of positive cases that we've tested, but actually that number of positive cases, it depends on the denominator here, which is tests in some sense. And so we're going to model the observed number of positive tests between times TL-1 and TL as a binomial realization of the total number of tests, where the probability of testing positive in that time interval is going to now be linked to the latent incidence in the model. And the way that we're going to do that is we're going to model this pi L using beta distribution. And the logit mean of that beta is going to depend on the log odds of individuals becoming infected or progressing from early, moving from early to progressed infection over that time interval. It seems like a little bit of an odd functional form, but it does kind of the right thing, because as incidence goes up, so too does our per test probability of positivity. And so here's how we link incidence to test positives, in other words, to cases. This delta NIEIP, this is a change in cumulative IE to IP transitions over the time interval TL-1 through TL. And then we have these hyperparameters. So looking here at the functional form of this, this mean model for the beta, if alpha 0 is equal to 0 and alpha 1 is equal to 1, then the percent positive in the testing pool is going to equal the percentage of the population that goes from IE to IP in that time interval. Now, we don't want to have the sample pi L here, so we can actually integrate it out. So we represent the observed number of cases as a beta binomial sample of the total number of tests. And just to give a little bit more intuition of what this functional form actually does, as alpha naught increases, the test positivity probability becomes much greater than the latent fraction of the population that moves on to progressive infection. So progressive infection is here actually sort of implicitly defined as when someone might become tested, might get tested, so when they develop symptoms. So there's this initial asymptomatic period. And so it accounts for, at least from a dynamical perspective, this sort of testing delay. Although testing delays at the surveillance level is, I think, still a hugely important question, and something that we have yet to address in this model. Similarly, as alpha 1 moves away from 1, so as it decreases, we see that the percentage of tests that are positive it kind of flattens out those curves, and it shifts them above the latent incident fraction of the population. So priors, we've got them. They were all well motivated based on rigorous lip reviews. We won't get into those now. So putting this all together in a modeling framework, we have the likelihood of cases and deaths, and conditional on latent epidemic paths, they are independent of one another. So the posterior, as is typical of a Bayesian model, factorizes is proportional to the likelihood times a set of priors. So we went through a bunch of trouble to develop this, and why is it useful? So this is just sort of a simple simulation in which we compared our model that's adjusted for testing to a standard surveillance model with no adjustment for testing, but that does allow for underreporting. And what happens when you do that is you just get them all completely confused between increases in tests. Oh, I should say also here we allowed for tests to increase with cases. So individuals were still preferentially tested but with underreport. And this is a relatively simple example, but if you don't account for testing, you're just going to get blown out of the water here for your estimates of the transmission dynamics. So coverage for the basic reproduction number when you don't account for testing in this simulation was like 8%, which is just awful. We were a little overly conservative in our coverage, but I mean, you're just going to get it wrong if you don't account for testing. That's sort of the bottom line. And looking here, we see that there's a lot of bias in the test unadjusted model. You also end up being way overconfident about, for instance, other aspects of the transmission model, like the infection fatality rate, while still being more biased about the IFR. So, yeah. So anyway, that's sort of the bottom line about that. So just a few results. We applied this model to 3 separate periods independently of one another for Orange County, so March 31st through early May through early June, and early June through early July. And then the model was homogeneous within each of those time intervals. And so we see after the relaxation of stay-at-home orders, R naught went up. The infection fatality rate was more or less stable, although in the month of June, or between mid-early June and mid-July, it did go down. That's concurrent with younger people tending to get infected as the epidemic wore on. The surveillance dynamics for cases were fairly stable over the course of the outbreak. Not too much changed, a little bit less preferential sampling as we went on. We're able to estimate the latent dynamics of the outbreak. And what we see here is that deaths tend to be somewhat underreported. Cases really much more so. And so I guess in the interest of time, we can also estimate prevalence using this model. And this is one of the advantages of integrating multiple data streams, is that certain aspects of the model start to be identifiable where they may not have been with just a single source of data. And so there are some extensions that we're chasing down now. And I think also a lot of important limitations that need to be acknowledged. So this is a complex model. Some of the parameters really are only weakly identifiable. And it becomes really important to lean on our epi collaborators and our collaborators who are hospitalists who could really shed light on the disease dynamics of COVID-19. The model is also complicated in certain ways, and so misspecification of any one aspect of the model can have consequences elsewhere. In particular, if you misscale a prior, you're going to see it. It's not going to crash quietly. It's going to blow up. And there are also computational challenges here. So right now, one of the important things we're working on is making this model fully stochastic. And there are a number of ways for doing that. We're chasing down a linear noise approximation for this. But anytime you introduce additional complexity in the model, you have to deal with the computational challenges. So the code is available here on this GitHub repository. We also have a manuscript that's should be any day now pushed to archive, and the repository will link to that. So that's it. That's what I've got.